Okay, so yesterday I give necessary tools to explain this mean curvature flow. So did you announce this? Oh, already?
Yeah. So we have the seminar of young mathematicians this afternoon at 5:45. So we have the title on the blackboard. So everybody is welcome.
And it's the other room, it's not the room 4.
Okay, so today I'd like to start talking about this tool. So this is Brakke's mean curvature flow. Okay, so first I'd like to give you what the explanation about what the mean curvature flow is for smooth case. So a family of let's say first let's start with smooth k-dimensional surfaces. Let's say MT, where T is a parameter. Let's see, maybe starting from time 0 and going to some time T is called mean curvature flow. Let me write this MCF. If the velocity, normal velocity, let's say V, let me write normal velocity as a VMT is equal to the mean curvature flow, to the mean curvature of MT at each time and at each point. Okay, so it's the so you have k-dimensional surface which is moving, and the velocity at each point of this surface is given by the mean curvature of that point. Okay, and now let's see. So it's well-known things. For example, if you start out with a sphere of radius, say 1, I just don't give you the precise formula or anything, but as you can imagine that, well, in this case of sphere, the mean curvature vector is pointing inwards. So the velocity and also the mean curvature vector has a length which is the inverse of the radius. So so the velocity as it shrinks become actually faster and faster, and in finite time it will become a point. So it vanishes in finite time. Or if you start out with something which looks like this dumbbell shape, now, well, I guess maybe I should have a long neck, but so in this case, for example, you have a very strong curvature inward in this thin neck. So in finite time, you have you have this kind of pinching where this become separated into. So you have this kind of singularity in finite time. And this is supposed to somehow kind of become separated, yeah, in finite time. So even if you start out with a very smooth surface, in finite time you expect that this surface become non-smooth. But what I like to do in this course is even more singular situation where you start out with something which is already singular, like something like networks, for example, like these things that I draw. And I want to consider the mean curvature flow of singular set even. And that's formulation that's given by Brakke in 1978 monograph. And this is something I'd like to explain. Okay. So first, let me first explain. So for singular object, how do you define the velocity? Okay. So let me explain how you might try to do this. So this is 2.9 is a weak formulation. Of velocity vector. Well, maybe I'll just say velocity. Okay. So you see, I have to do everything in terms of integration, and how do you do it? Okay. So again, just to motivate this weak formulation, let's assume that we have again smooth object mt. Okay, with velocity v of mt. Okay. Now, let me write this just as v, okay, just for simplicity. So when you try to do weak formulation, you have to do, you have to have some test function, and let phi to be a test function, which is a C1 at least, and maybe everything. It doesn't. This doesn't have to be defined on the whole entire Rn. So let's say we are looking at some U, which is could be Rn, but could be some bounded domain. Okay, and so let's assume that the phi is a function defined on U, but also take a time variable. Okay, and non-negative value. Okay, so there's some reason to restrict myself to a function which takes a non-negative value. Okay, so has a compact support in space and time. Okay. Now, so this acts as a test function. And let's see what happens if you are looking at the change of the integration. Okay, so what we like to look at is there aren't that many things you can do. So you integrate this test function, okay, and let's look at what is the rate of change of this. Okay. Okay. So do this computation, and let me quickly tell you what is the result. Now the result is that this comes out to be this. That is, the first you have a time derivative, and then the next term is the phi dot v, and the last term is phi times h dot v, where h is the, so maybe I should also h is h of mt, so shorthand for that, and that's all. Okay. So first, I have to explain this formula. It's not so difficult from what we have seen already. This first term is just how this test function changes in time. You have to differentiate this one. And the second term is something similar. You see, this empty is moving, and so you have to take into account the change of this phi in the direction of the motion. So that's a sort of a directional derivative of phi in the direction of v. You see, that's the direction that this guy is moving. And the last term is a bit more complicated, but this is the differentiation of how the area element is changing. Okay, so that this is like a time derivative of Jacobian, and which you end up having this mean curvature contribution. So I don't carry out the computation for this, but I think you can imagine this is something like this. That is, it's more like first variation formula here that you do in the direction of v. So you see, if you have this motion, well, here I'm not talking about mean curvature flow, but any sort of general motion of surface with velocity v. Okay? Not talking about mean curvature flow yet. Okay? So I hope this is okay. So now this is true for any phi in this class. Let me write this class as, let's see, what would be a good term? Maybe E, okay, just for simplicity. Let me call this class of test function as E. So any phi in E. Okay. This should be true. Yes?
Your gradient there is your gradient in the ET?
This gradient is with respect to x.
But it's not a tangential gradient in there.
Oh, no. Yeah, it's just, no. You see, if it is, then no. It's just a full gradient. Yeah. But you see, this is like a directional derivative in the direction of v. Yeah. So it's really like you're measuring how v is changing in the direction of the motion. Okay. That's right. Yeah. It's actually sort of important that this v is normal to this moving surface. Yeah. So v is okay. So can I erase this? Fine. Now I'd like to claim that the claim here is that, in fact, this characterizes, in fact, the velocity vector, but with slight difference. So the claim is v. Well, okay. So let's suppose that v is any normal vector field of MT. Okay. Suppose that v tilde is any normal vector field, not necessarily perhaps velocity vector, but some vector field. Then v is equal to this velocity vector v, if and only if if and only if this things that I wrote, ddt mt phi, this is less than equal to this, the right hand side, minus 5 h dot v. Let's see. Maybe I should have v tilde. Okay. For all test function. Okay, so that's something I'd like to claim. That's my first claim. Okay, now notice that here is an inequality, not equality anymore. Okay. If v tilde is equal to the velocity vector, normal velocity vector, I just show you that this is true for with equality, right? As you see. But the converse is also true. That is, if for any phi, if this inequality holds, then this v tilde has to be equal to velocity vector. So let me check that's true. And I'm doing this just to motivate, how you define the velocity vector in a weak formulation. This is because everything here is written with integration. Okay, so why is this so? So proof. So this is my first proof in this lecture. Yes.
Your MT here in the integral they are generated by the flow on V.
Oh, so, the velocity of this?
Yes.
Yeah, I am making a notation that this is the velocity vector.
Okay.
Yeah. Okay, so here.
Okay.
So yes, so here mt is moves by velocity, normal velocity v. So yeah, so this guy is moving by velocity v, and suppose you had a velocity, suppose you had a normal vector field satisfying this condition, then that has to be velocity vector. Okay. I hope that's clear. Yeah, fine. So let's see its proof. It's, so by the way, I'm assuming everything is smooth at this point. Yeah, it's just motivation. So, so we know already that V satisfies this already. The velocity vector itself satisfies this equality. So this one, yeah, maybe I should just start. So let's see, and assume that so all I have to prove is, of course, this implies this. Yeah. So let's consider let W to be a difference, okay, V tilde minus V. Now we know that the V satisfies that one with equality. The difference, well, what is going to be the difference? You see, the difference of V tilde minus V, well, the left-hand side is the same, right? I mean, this doesn't involve any V or V tilde here. This one doesn't. So you see this guy here and V tilde here. So the difference, W, is going to satisfy this inequality. That's mt and nabla phi dot W minus phi h dot W. Okay? So this has to be satisfied by any test function, phi. I think that's, I hope that this is clear. You see, V satisfies this with equality, so the difference is going to satisfy this inequality. And now, okay, so all we have to prove, we need to check prove that W is actually equal to 0. Then we will be okay, right? I mean, then that shows that V tilde has to be equal to V. But why is that so? Because you can do the following. So just choose any point. Okay, take any point, and let lambda to be a parameter, any parameter, and take any phi. Okay, and then you do the following. Okay, you just do the following. So you just define phi lambda of x to be defined as lambda to minus k plus 1, and a phi of x minus x0 divided by lambda. Okay? You just define this function. And you plug this in into this formula. Okay, then you see that, so this, if you define like this, then the nabla of phi lambda, this would be, well, you differentiate this x once, so you end up having lambda minus k of lambda phi x minus x0 over lambda. One lambda is cancelled. Okay. Now you plug in. Now the one note that this one and this one has a different lambda power. Well, this one has lambda minus k, while this one has lambda minus k plus 1. So what you can see is that if you plug this in, then you end up having the following inequality. So lambda 1 over lambda k mt and number phi of x minus x0 divided by lambda dot w of x dhk. Okay. So that's the I'm writing this first term. Now notice that this one, if everything is smooth, this term is actually you have this guy. Now notice that you have lambda minus k plus 1. So this one has end up actually having the order of lambda. Okay. It has a different order. Well, by the way, lambda is the one that goes to 0. So this is small term if lambda goes to 0. And do the change of variable here. And then you see that so we do a change of variable. Let's see. So let's say z is equal to x minus x0 divided by lambda. And then you end up having the following, that 0 is less than or equal to integration. Now, after this change of variable, you'll be integrating the place where z is in this mt minus x0 divided by lambda. Okay, that's the place where you'll be integrating. And here's a lambda z dot w of lambda z plus x0 after just change of variable, and dhk. And now this integration with respect to z, and plus order lambda. That's just this change of variable kind of kills this lambda to minus k. And if you let lambda goes to 0, in the limit, let's see. So this guy is converged to just a tangent plane of the this mt, okay? And this becomes just a constant x0 as lambda goes to 0. So you end up having this inequality. That is, you have a tangent at x0 mt and phi z. Now notice that once lambda goes to 0, you don't have this guy. So this is like a constant vector after lambda goes to 0. So I might take this outside of this integration. So here it's x0. Okay, you have this in the limit. No problem. I hope that's fine. Now, so now you see this guy. What is this guy? Notice that this is the integration of. So actually, this is a vector, of course, and but for each vector, notice that this is the integration over the tangent, so flat place. So by the divergence theorem, you do integration by parts, and you can see that this vector field is in fact in the normal of this tangent space. That is, the tangential part becomes 0 after integration by parts. Okay, I hope that. Well, if suppose this is like RK. Okay, maybe easier way to see it. If this is RK, then any derivative j where j goes from 1 to k will be 0, right? Okay, the rest is going to be just a component which is normal to this RK. Okay, so now this is has to be true for any phi Now, here the phi has to be non-negative function. That's actually was somewhat important part. The phi is non-negative value function. But you can choose this vector to be whatever you like in some sense, because you see, you just have to cook up some vector which is in this direction, pointing out this direction. And remember that this is a normal vector too. Okay, so this belongs to the same place. It's the normal velocity, the difference of the normal vector field. I'm sorry, this is not normal velocity, but that's what we wanted to prove. So, but yeah, we know at least that this is a normal vector field. So this shows that in fact, if this has to be true for any phi, then W has to be equal to 0. Okay, has to be equal to 0. So actually, that inequality is it does characterize the velocity, normal velocity. So, and maybe you may wonder why you care about this inequality. There's some good reason, which I'd like to explain later. But anyway, so this characterizes the velocity. Let's see. When did I say? Okay. Right. So okay. So let me write this as a proposition. Okay. So so the proposition we find is that if you integrate in time, then that we can claim the following. So suppose MT is a smooth k-dimensional surface with normal. Oh, let's see. Okay, surface. Then just a moment. Then the normal vector field. Okay, so then the normal vector field V defined on MT is velocity of MT. Well, if and only if for any phi on E and for any time T1 and T2, this is true. Okay, MT of phi DHK. So let's see, this at t equal to T1 to T2 is less than equal to the T1 to T2 dt and MT, let's see, d phi dt minus plus, I guess, plus nabla phi dot d and minus phi h dot d dhk. Okay, so that's something I can claim, because you see, if you integrate in time from T1 to T2, this is what you get, right? That is the inequality I wrote over there. If you integrate from T1 to T2, you have that by fundamental theorem of calculus. And this is just the integrated form of what we had on the right-hand side. Now, going from this to differential expression is also easy if everything is smooth, right? So this characterizes the velocity vector. Okay. So this is nice because everything is expressed in terms of integration, and we now use this to define the velocity vector. Okay, so the next one, So I interpret everything with the language of the varifold. So velocity for varifold. So this, I don't think it's written anywhere so far. So this is quite kind of new notion, I guess. But maybe implicitly it was used somewhere else. So let me define. Definition is a family of varifold Vt. So T could be, I mean, I don't want to be too specific, but let's say T is defined on this interval from 0 to T, which is a general varifold, say on U, moves by generalized normal velocity V, which I assume is to be in L2 class, locally L2 with respect to the weight measure dt. Okay, so let me explain this more precisely later, but first let me write the conditions. So I'm not still talking about mean curvature flow, but I'm just trying to give you the correct definition of the velocity of motion for varifold. Okay. Later, I specialize in the mean curvature flow, but now it's still quite general formulation. So if there are a couple of conditions. The first condition. So by the way, this is not a standard, definition because there wasn't any, I think, for varifold related so far. So this is reflects my taste in some sense, and also my experience, I would say. So it could be different, of course, but yes.
Sorry, I wasn't here yet. So that the double bar is
Yeah, it's a
mass?
yes mass measure or weight measure. Yeah, right. So let's see. Yeah, maybe I should say that. Okay, so when I wrote this L2 log Vt dt, this means that let's say locally v square of dt, let's say 0 to something like t. Well, it doesn't have to go all the way to t, but this is less than, it's finite. Okay. And as I said, this is, so if this is a weight measure, so you can think this as a k-dimensional measure restricted to mt, if you like. If you want to just think of something smooth, that's what it is. So if I say this, that's what I mean. But the number one is the condition is for almost all time. For almost all time, I want this varifold to be integral. Okay, I want this to be integral varifold. Just to be relevant to geometric problem, I would say. I mean, if this is not true, well, I guess you could talk about other kinds of flow, but I want to be somewhat geometric, and being an integral varifold is a natural kind of class relevant to geometric problem. So number two is for almost all time, Vt has a locally bounded first variation. Boundary first variation. And also it's absolutely continuous. absolutely continuous with respect to the weight measure. Okay. So this means, roughly speaking, there's no boundary of this moving MT. Okay. And also, as I explained yesterday, if it's absolutely continuous, then you can define a generalized mean curvature vector. Okay. So this condition gives you almost everywhere you have well-defined. Let's see. Let me write this as h of Bt, which I subsequently may write as h. Okay. You see, if it's absolutely continuous, well, actually, you don't have to have this, but I don't want to have any boundary appearing, so I'm assuming this is true, and then I have this first, the generalized mean curvature vector. Yeah, sure.
So the interval, what you want is rectifiable and an integer multiplicity?
Integer multiplicity, yes. Yeah.
So rectifiable and integer multiplicity.
Yeah, that's right. That's right. Yeah, yeah. And third, so you have this generalized mean curvature vector. I want this to be L2. Okay. L2 with respect to the space-time L2, or maybe it's local. Okay, so I want this mean curvature to be in L2. And the 4, there are 5 of them actually. So 4 is the density upper ratio bound. No, sorry, the normal. Yeah, sorry, normal condition. Right. Okay. So for almost all time, and Vt almost everywhere, Xs, GKU. I want this V to be normal. V of xt, I want this to be normal to the tangent somehow. So this has to be equal to 0. Okay. Or I may write this as S perp of V to be V. That's the same thing. Okay. So, okay, I hope this is not confusing. So this tells you, in the language of varifold, that the V is normal to the tangent. Okay. Okay. That's. Let's see. Maybe I should say a bit. Yeah, it's a bit too much. But maybe. So you see, for almost all time, I know this guy is an integral varifold. So Vt has this kind of expression, theta times some underlying rectifiable set. Okay. Then this is saying that is that almost everywhere since the Tx of Mt, so V is in this in the normal to the tangent. Okay. That's all what this is saying. Okay. So the number 4 is really specifying that this the V has to be in the normal normal space. And the last one is the inequality that characterizes the velocity. Okay, so phi is for all phi and for all time. It's the same thing, T1, T2. We have this inequality that phi of dVt, where t is from T1 to T2, is less than or equal to T1 to T2 dt, and the same thing, d phi dt plus nabla phi. Okay, let me put this together. Phi h dot v dvt. So this, well, this is the what we had before, but written with the language of varifold. You see, this is nothing, as I said, as if everything is fine, then this is hk restricted to mt, and that's the same here too. Here, h is the mean curvature, generalized mean curvature that I assume that it exists. Okay, and since it's L2, and also I'm assuming that the velocity is L2, this is integrable. H dot v is integrable. Okay, this is L2, this is L2, so it's integrable. Okay, so that's all. So that's the notion that you can define for the varifold, the velocity for a varifold. And finally, okay, so that's finished. So finally, the definition for Brakke's mean curvature flow is that, well, if this V is equal to the mean curvature, then it's Brakke's mean curvature flow. Okay, so the definition. So if, let's see, so the definition is when this family of varifold, this family of varifold has a generalized velocity v, which is equal to mean curvature Vt, then this Vt is called Brakke's mean curvature flow. So that's the definition of Brakke's mean curvature flow, stated somewhat differently from the standard Brakke's mean curvature flow, if you know that. Yeah. Somewhat different, but actually equivalent definition. Yes?
You said that Vt can be with multiplicity, integral multiplicity, but it can vary with the time, or not?
Yeah, theta can vary, in time. You mean, this one, right? Yeah, this depends on the Vt, of course. So theta depends on Vt. So yes, it can vary. Yes. In principle, I mean, I'm not claiming that it does change or not, but yes. Okay, now I hope that's not too bad. And by the way, this condition. So first remark is that this number 4 is in fact is redundant for Brakke's mean curvature flow. So this number 4 is this normal condition. This is because, well, since I hope that I'm not making some strange claim, but suppose that this V happened to be equal to the mean curvature vector, because of the perpendicularity theorem that I explained at the end of yesterday's lecture, by Brakke's perpendicularity theorem, this V, which is now is mean curvature, is actually normal to the tangent space, okay? MT, where MT is is given in this relationship. Okay, I should pressure MT. So in fact, this number 4 condition is not necessary in this case. Okay, so that's I wrote it in case you have more general flow, then you may not have it. But so this is so number 4 is somewhat redundant. So that's one first remark. And maybe answering your question, I also want to define another extra condition, that another definition. So sorry, lot of definition. If this varifold, family of varifold is Brakke's, so that is Brakke's mean curvature flow, is additionally satisfy this additional property. Let's see if V satisfies the following, that for almost all time, if Bt is unit density, okay, that is this theta of T, maybe, I don't know how to express this, but of Bt is actually equal to 1 almost everywhere. Okay, this multiplicity function is equal to 1. Then I say satisfy this. Then let's see, we say this flow is a unit density Brakke flow. Okay, it's called unit density Brakke flow. Okay, Brakke's mean curvature flow. Maybe I write BMCF. Okay, so that's called unit density Brakke mean curvature flow. So this is just a definition. Any questions? I think I defined many things. So at this point, maybe I stop. And time-wise, I don't probably want to stop here. But any questions at this point? Yes.
It was just that you erase it, so maybe when you write S of Vt equal to 0, you see S as a map, because it's for me S is a K subspace of K-dimensional subspace of
Right,
and
yeah.
you see it as the orthogonal projection
Theta, yeah.
on V. No, you apply
Theta, this one?
No.
Ah.
You the fourth condition.
Yeah, this one, yeah.
You write this equal
Yeah.
to 0.
Mm-hmm.
When you say S of V, is S as the orthogonal projection?
Oh, yes, exactly, yes. Yeah, that's the way I understand. Yeah. So this is really, what I said was, if you project to the tangent space, that's equal to 0. That's what it is saying, yeah. So V of xt equals 0. Okay. Any other questions?
Something like this exist, because you're asking the...
Yeah, I am asking many things, yeah?
But you're asking about the density to be 1.
Right.
Everywhere.
Yes.
How do you know if it's target of 1?
I know, yes, that's a problem. I'm going to talk about it. Yes. You know, I asked so many things. You wonder if this exists. So, yes, of course. So, yes, next, so naturally, you have that question. That's, of course, natural. So, let me explain about the existence part of such things. Okay. So, the next things I like, well, I think before I stop, maybe, or maybe it's a good time to stop, perhaps. Did I say 2? Oh, I started 2:30. 2, huh? 2 o'clock, did I? Yeah. Okay. Before I go to existence theory, just let me make a few remarks. So maybe remarks further remarks about Brakke flow. So, well, if I assume that this support of this Vt is in some ball of radius r, so suppose that this guy is bounded flow, then we might take phi to be essentially equal to 1. Okay, just if you use this phi equal to 1, well, this doesn't have a compact support, but of course you can change phi to be 0 outside of this ball or something. And then this brackets, the inequality that I wrote is going to be just a Vt of Rn, where t is from t1 to t2, and that's less than or equal to t1 to t2 dt, and now d phi dt is 0, nabla phi is 0, so the only one that's left is minus phi, and now v is equal to h, so this becomes h squared. Okay. So this basically tells you roughly, well, if you write this in a differential form, d dt of the total mass. Yes, okay, so this implies in a differential form, well, whenever you can differentiate, is less than or equal to minus of, phi is 1, by the way, so that's right. Phi is 1, so you don't have to write. And h squared dvt. Hope that's correct, yeah. So this tells you that the rate of change of mass is proportional to the mean curvature square, which I think if you have seen mean curvature flow, this is what you have with equality if everything is smooth. But here we are asking this to be at least inequality. Okay. So so its mass is decreasing flow. That's important. And also next, just a trivial remark is that when you have, so the second point is if v is dt is equal to b, which is the integral varifold with stationary varifold. Okay, then of course this B is Brakke's mean curvature flow. Okay, because if this means h is equal to 0, because first variation equal to 0 means the generalized mean curvature is equal to 0. So trivially, this satisfies all the conditions I wrote. Okay, 1, 2, 3, 4. One is, well, it's integral for all time, in this case, trivially. And the second, you have well, anyway, so yeah, and this inequality is also satisfied with h equal to 0. So any stationary varifold is actually a solution to this Brakke's mean curvature flow. Okay. And also I should say why we have this inequality. So reason for this inequality, not inequality, why we have this inequality. Well, there are a couple of good reasons, and well, there's a sort of couple of geometrically reasonable geometric reason. Well, one is the this is well-known kind of reasoning. So suppose you have two circles, one is bigger than the other. If this is flowing with mean curvature flow, what happens is that, well, this guy has a smaller curvature, while this has large curvature. So this guy shrinks faster than this larger one. Okay? So here, actually, to have a reasonable curvature here, you have to have a 120-degree junction here, but just for, well, I don't care too much about detail, but so this guy develops. After a while, it becomes this smaller circle shrinks to a point. And at this point, what happens is that okay, so once this happens, well, I didn't explain this very well, but you have a first variation which is sort of singular with respect to this one-dimensional measure. You see, this is a point, sort of delta mass of first variation here, which is not L2. Okay, that's a delta function, is not L2. So you have to do something about this. And the one way to deal with this situation is to eliminate this entire line section instantly. At the, when you have this situation, at that moment, you eliminate this portion completely. Then you continue. You can do it. Okay. So but this vanishing of this portion, you can't keep equality. You have to have inequality in this case at this moment. So that's one geometric reason that you may want to have this inequality instead of equality. So and the other, and I would say this is more. So, yes. Well, it's not so clear. That is well, you might say, well, that's the end of the story. Okay, if this happens, you may say, well, that's it. There's no more solution. But if you want to have some reasonable flow after this happens, that's one way. That is, at least you can't keep this keep a configuration like this, because suppose that if this stays like this for some time, you see you have the first variation, which is delta mass, which is not L2. But the one that, then the point is, if you have a point mass which is not in L2, this integration is going to be infinite. So the mass has to the entire thing has to vanish right away. Well, I don't know how to put this. You see, to have this formulation correct, you need L2 mean curvature in space-time at least. Okay. So at some instance, you are allowed to have delta mass of mean curvature, but not for some long time or short time. I mean, one instance you can deal with it because you are integrating in time, right? But you can't keep this kind of boundary for some time, for some open interval time. I hope that makes sense. Yes?
Okay, maybe I'm missing something, but let's say I have Vt, which is a family that satisfies Brakke's definition, and now I just make time twice faster.
Mm-hmm.
Then, so it's a movie and the movie is just going faster. Then in
Yeah.
some sense that rate is multiplied by 2. So the inequality is still there, right?
Yes.
Which means that if you scale in time, a solution is still a solution? Make it quicker?
Well, then you're having a different sort of motion law, no? You have to have velocity multiplied by 2.
Yeah, well, okay,
Yeah.
I know that wouldn't be in the definition, but is it admissible? What happens to the definition of solution? Yeah, right. This would be wrong in some sense.
Yeah.
Right? Because that's,
Okay.
I would double the velocity.
Mm-hmm. Yeah.
But if I look at the inequality there, that's still true. Because I doubled that one, which is negative, and this remains the same. Or am I saying something?
I don't quite understand. Maybe.
Only this is just for one vector, for just one test function. So
Okay.
for different test functions, it
It
reveals
fits.
that's really not the.
Okay, maybe, yeah. That's pretty, yeah.
Okay.
Okay, so, well, that's one reason to have inequality, but more practically, there is some more sort of practical reason to have inequality. And in fact, I don't want to have inequality, in fact, if it's possible, but quite often you cannot avoid it. It has to do with the existence of this flow. So it's a bit technical point, but I should just quickly mention that the reason of having inequality is that, well, the way you construct this kind of varifold is that usually it is some kind of approximation scheme. So you have a sequence of some smooth, say, mean curvature flow, and you want to in the limit you get this Brakke's mean curvature flow. That's the way you kind of construct the Brakke's mean curvature flow. But in this limiting process, what happens is that so maybe for this approximating one, you may have equality, but as you pass from this smooth guy to the limit, you have some you have to control various quantity, but the quantity you have problem is this mean curvature square term. Okay, so this one, well, usually has a lower semi-continuous property. So this kind of things is you only have usually the lower semi-continuity, and as even though this guy may satisfy Brakke's inequality with equality, the limit may not have equality. Okay, so this is sort of nonlinear kind of situation. I think if you have this kind of nonlinear problem, I suppose you always have this kind of problem. It's like Navier-Stokes energy inequality too. For smooth Navier-Stokes, you have energy equality, but in the limit you lose it, right? Typically, and it has to do with regularity of the flow usually. So it's a somewhat similar situation here too. So this having inequality, in some sense, has to do with the regularity issue of this flow itself. Yes.
Is it possible if you have formation of singularity to the mean, try to characterize and look it for magnitude?
Yeah, that's one. Yeah, interesting question. That yes, but yeah, there is a certain situation where things stays equal. For example, I don't have time to talk about it, but if you're doing mean convex case, actually it's known that this holds with equality for mean convex flow. That's one class.
So it's possible to quantify the term to the lack of equality. What it was.
Well, yeah, it indicates the occurrence of the singularity suddenly. Yeah, something has to vanish or something if that happens. So, yes. So that's an interesting point. And also, I should say that because of this inequality, just by itself, the Brakke flow is very non-unique, in fact, because, for example, I just say by words, so suppose you have a Brakke's mean curvature flow. Now you can do the following things. At some point t equal to, say, t0, you can just decide that this Vt is just empty, or the zero measure. Okay, so the other point, maybe I just write. So if suppose you have a Brakke's mean curvature flow, now that t equal to t0, you just redefine Vt, say, so up to t equal to 0 to t0, you have the same thing, but later you just assume that's t0, okay? So given this Brakke's mean curvature flow, you can define this V tilde t, the new Brakke's mean curvature flow, as up to t0 the same, but after t0, 0. This is also Brakke flow because it becomes 0, this inequality is satisfied trivially. Okay? So in this sense, it's very, very non-unique. But of course, this is something you don't want to do. It's kind of silly to just do this. So in fact, if you're just looking at Brakke's mean curvature flow, as I wrote, it's non-unique. Okay, very non-unique, in fact. And so you need some extra things to make sure that the thing stays unique. And this extra things is not still so clearly understood, I think, in my point of view. Okay, so there's a lot of open questions about even the definition of this mean curvature flow. Now, next I'd like to tell you about the existence. So as I said, does such thing exist? Okay, so but it does exist, and so this 2.4 existence. So so there's first one is original proof due to Brakke. So Brakke has this book, which is from '78. And in the first part of the book, he shows the existence of this Brakke's mean curvature flow starting from any varifold, actually, even general varifold, with some condition, minor condition about the support of the varifold. But you can even start out with non-rectifiable varifold even, in fact. There is some kind of difficulty about this. Well, first of all, it's very difficult to understand this theorem, the proof. It took me quite a few years, and actually I'm kind of rewriting this part now with my postdoc, Lami Kim, who is there, yeah, working out, doing some kind of detailed review of this. And also the other thing is it's not so clear if the solution he gets is non-trivial or not. I mean, you see, 0 is a solution. So you don't know. If you start out with something quite singular, maybe right away it may become 0, right away, instantly. That's a solution. So you can say that the solution exists in that sense, always, because 0 is a solution. So, but that's of course not. You think that as an existence theorem. So, but anyway, so we are actually trying to make some kind of fixing of that point now. But anyway, so that I don't want to talk about this much. Now the next one is a viscosity solution. So this one is actually very nice. This is viscosity solution by Chen, Giga, Goto, and Evans Brakke. So this is a scheme of constructing a mean curvature flow for hypersurface. Okay, so I think I just quickly mentioned that the U is a function defined on the entire Rn, and the real valued. And the scheme of this viscosity solution is to get a mean curvature flow as a level set. And so I just quickly say this. So you prove. So if the level set is moving by mean curvature, it's not so difficult to check that formally at least this should be satisfied, okay, with a given, let's say t equals 0, even as u0, because this corresponds, the left-hand side corresponds to the velocity of a level set, and this is a mean curvature of a level set. Okay, so that's if this is equal, that means it's a mean curvature flow. And because of this degeneracy, you see, of course, when the gradient is 0, you have a singularity. So you have to define this equation with using the notion of viscosity solution. I don't want to go into this, but one thing, very interesting thing that was proved by Evans and Brakke is that. Well, I don't state this very precisely, but Evans and Brakke proved that if this u0 is some kind of distance function from some C2 surface, well, I should say maybe more clearly, it's a signed distance function, but it doesn't matter perhaps. But so suppose MC is say C2, okay, so it's actually smooth, well, smooth category kind of things. But Evans and Brakke proved that then for almost all level set, is in fact Brakke's mean curvature flow. Okay. So this is a formulation where you have a level set. Each level set is supposed to be formally at least moving by mean curvature flow. But because of this viscosity definition, viscosity solution, you don't really have the pointwise information. In fact, you define this by using the maximum principle. But what you can prove is that almost all level set, not all level set, but almost all level set is in fact Brakke's mean curvature flow. So this is the one answer to Tatiana's. Actually, it does exist, at least for hypersurface case, except that, well, you have this kind of genericity of, you can't say it's all level set, but almost all level set, at least is Brakke's mean curvature flow. So this is a good, and also the other thing is this is actually unit density too. Unit density Brakke mean curvature flow, just because you see it's defined as a level set, so naturally its density is equal to 1 almost everywhere. Okay, so and this is nice, very nice result, and in fact this is pretty much the only result of existence of unit density Brakke mean curvature flow. In fact, that's very much the only thing known. Okay, and the others. So that's maybe I should have put B. So the C is this is a so-called phase field method or reaction diffusion method, which I'm going to talk about a little bit about this in the third and in the fourth and fifth lecture. So this one is due to Ilmanen. Maybe I should write this 93, and also I did a bit of that part, so 03. So this is the approach where I'm going to talk about this more in detail later. But so you consider this so-called phase function. And epsilon is a small parameter. Okay, so I just write this and don't explain too much. But this W is so-called double well potential, where this W has a local minima at -1 and +1, like that. Okay, and then you consider the parabolic equation gradient flow. So what you do is you solve the parabolic equation, Laplacian phi minus W prime of epsilon square, where and also when t equals to 0, some appropriately given let's see, initial data which also depend on epsilon. Okay, and this one I can't explain too much now, but just say that so this has this is a very nice method to get a mean curvature flow, and so somehow I just say like a keyword that actually this phase boundary as epsilon goes to 0, goes down to 0, converge to Brakke's mean curvature flow. Okay. But so I probably don't have too much time to explain this. So the one that you get for this is precisely Brakke's mean curvature flow. But this case, you may have multiplicity, maybe not unit density. In fact, there is a possibility of having this theta of Vt, in the limit, maybe bigger than 2. That's a possibility. And in fact, you can construct such things. In fact, you can construct the Brakke's mean curvature flow, which has higher multiplicity. Well, if it's bigger than 1, I would say higher multiplicity. But you can construct such things as a limit of this problem. And I will explain this. So don't worry about this one. But I just wanted to say that as a limit of this problem, you do get the Brakke's mean curvature flow also. And I just mentioned that the Ilmanen prove that the limit measure satisfies this inequality. And the one I did is I showed that the limit measure is actually integral also. But the integrality is somehow important from point of view of the regularity. So, and let's see. So, and I should say also as a D, this one is a more recent one. Now, using this technique of this phase field method, I also proved with this one is with Liu and Sato and myself. This was first one is 10, and also I have recently paper with my student Takasao and myself that just accepted recently. But so this one is somewhat more general flow than the mean curvature flow, and so this one is if you're given the vector field U, which belong to LQ. So I'm sorry, this is a little bit looks a bit technical, but somewhat interesting from regularity point of view. So if you are given a vector field U, so this is actually vector field. Okay, U is a vector field with space regularity in W1P, and a time is LQ. Okay, LQ W1P, where P and Q is I don't specify what this is, but it's a sort of subcritical. Critical. There's some nice some natural condition that from a dimension from a dimensional point of view, there's some condition you should put on that. Then you can construct solutions. Brakke's mean curvature. Well, actually, sorry, it's not Brakke's mean curvature flow, but you can construct the flow. You can construct a flow which has this property that the velocity is equal to mean curvature plus u, but with normal projection. Okay, to the so you can construct this. Okay, so in the generalized sense, so the velocity satisfying mean curvature plus this given vector field. Okay, so it's using this phase field method, where here is some sort of you need to put this extra term. So that's more for as a passing note that you can also construct some more general flow within this kind of framework. Okay. Sorry? U is the so this is more like a normal projection. You see, this has to be normal velocity, right? So I have to project u to the normal direction. So I'm actually really this is a shorthand of doing this S perp of B, in fact. Okay, where S is the so tangent of the varifold. Okay. So I'm not explaining very well about this, but I'm just saying that there is a fairly wide class of flow that you can construct with this kind of framework. Okay. Right. Okay. So in the maybe remaining 5 minutes, I just mention quickly about what's known on this flow. Okay. Now, so maybe I should say 3 is a regularity of Brakke's mean curvature flow. Now, for this, even before talking about this Brakke flow, it's good to talk about the static case. Okay, that is the static case. that is a case where Vt is just V, where the first variation V is equal to 0. So it's a stationary integral varifold, as I said. It's a case where, it's nothing is moving. It's just stationary integral varifold. Then what do you know? So in this case, V is just some multiplicity function times some countable K rectifiable set. So this means, I hope this is clear now. Theta times, there's some countable K rectifiable set. Then in this case, there's this Allen's regularity theorem. Now, maybe I wonder, maybe I should just talk about the unit density case. That's pretty easier. Well, maybe. OK, so essentially what's known, even for this setting, is it's not quite precise, but what's known about the regularity of this object, where the first variation is equal to 0, is actually if you have a multiplicity, it's very difficult to say anything, in fact. And what's known about this is, so essentially, what's known is about unit density case. Okay, so unit density case. That is, theta is equal to 1 almost everywhere. Okay, so maybe I should concentrate on this case. I mean, it's in case higher multiplicity that you can say something, but it's not so essentially different from unit density case. So maybe I'll just say a word about this. So let me repeat. So in case you have this theta, 2, 3, 4, and so forth, there's something you can say, but not much. So I just say that in case V is equal to this, and the first variation is 0. Okay. Now here, the point is there's no minimizing property or nothing. All we know is just first variation is equal to 0. That's all. Okay. Then what can you say? Now in this case, there's this Allen's regularity theorem. Which says that the support of V, okay, so may contain some set S, and well, S pro is not a good thing to use. Maybe C, which is a closed set. Okay, so support V has a closed set, and this closed set. Okay, so there might be some closed, which could be empty, of course, but in general may not be empty. And this guy has measure 0. So k-dimensional measure of this closed set is 0. And outside of that, well, V, outside is a real analytic minimal surface, or k-dimensional minimal surface. So there is a 0, there might be a singular set. Of course, something like, this extremely simple things like this, you have singularity. Okay, so there might be a singular set, but that's a closed set with measure 0, k-dimensional measure 0, and the outside it's a regular, smooth, real analytic local area minimizing. In fact, in a small neighborhood. So it's sort of nice, but with singularity. now, so that's something that you can say. Any questions? It's okay. All right, and so what one hopes to get is analog of this, hopefully, for mean curvature flow. But of course, you should note that there may be singularity. Even static case you have singularity, and of course you can't hope for something better than this case because this is a Brakke flow after all. So you can't get something better than this. Yeah. So what I'd like to do next is so I'll stop here. But what I'd like to do is to present my recent work. So this is a regularity theory. Regularity theory for unit density. Brakke mean curvature flow. Okay. And which means the multiplicity function is 1 almost everywhere for almost all time. Then this result, I should say that this result has been somehow claimed by, first claimed by Brakke himself. Brakke in his book. But the proof was, I would say, was never understood well, this regularity theory. And there does have a serious error, in fact. And so what we did is we recently gave a completely new proof. So this is something I did with my former student, Asai, and myself, which appeared just last year. And also another paper dealing with higher regularity. Okay, so this gave a new and also more general regularity. Results. Okay, and so next lecture I'd like to discuss just a bit. I can't really explain everything, but just some of the sort of highlight of the proof, as well as the statement of the proof, statement of the theorem. And also I should mention that this Brakke's proof, Brakke's original proof, has been also recently reviewed by proof is recently reviewed by this one of the person here is Lahiri. I'm not so sure. Lahiri. Okay, sorry, forgot. Sorry. Lahiri gave in his doctoral thesis. Sort of rewrote the entire Brakke's flow along the line of Brakke's proof. So very different from my proof, in fact. That's a very nice, very long paper. Huh? It's almost like 200 pages or something. Yeah, it's quite a big work, but yeah. So he did very nice things, and so. I'll talk about this, but ours is more like Allah's regularity theory in some sense, using a blow-up argument, and Lahiri's proof is really following the Brakke's more constructive kind of proof, not using blow-up argument. So it's hard theorem. And so next time I'd like to explain more about this. Okay, thanks.